So hello everyone, and welcome to the new reading group, which is called Practical Networks. The idea of this reading group is to be the complement of the network theory reading group. So here we are going to address topics more closely related to the practice of networks. And today is the first talk of this reading group. And I'm going to talk about vehicular networks. My talk will be a tutorial talk, but in the group we welcome talks about a paper, about a topic, about a demonstration, about basically whatever you would like to share with the group. The rule is that you are not supposed to present your own work, but to share with the others something you are you stumbled upon or you are working on and you are learning. Okay, so I think this is new time for the reading groups this year. So they start at 11:30 and not at 11. They happen on Wednesdays, and so there is a rotation between this reading group, the network theory reading group, and the Python working group or reading group. Okay, so I guess this is all, and I will start with my talk. And as I said, I wanted to talk about vehicular networks and practical aspects of vehicular networks. And I wanted to talk about these aspects in relation to the radio access technologies that are chosen to power these networks. So, well, the theory of vehicular networks is known, I guess, to everybody in the room. So, the first thing that you can build are ad hoc networks, which are networks without an infrastructure. The first application, the first example that you can think of is a wireless sensor network where you deploy sensors, in an environment, and they need to be able to communicate without having a fixed infrastructure in place. You can complicate things, allowing these nodes to be mobile. So you get what is called a MANET, a mobile ad hoc network. The problem here is that the network is going to need to be able to reconfigure itself because you have this dynamic behavior of the nodes. And then vehicular ad hoc networks can be thought as an extreme version of MANETs. So you have nodes that move at high speed, and you have large mobility. You have very unstable neighborhoods. So if you look at the picture, you have the neighborhood of the blue car. So in the neighborhood, you have two other cars, and also what is called an RSU. It's an infrastructure piece that is able to communicate. And so you have four nodes in this neighborhood now, but what happens is that blue will move forward. So the purple one will enter the neighborhood, the red will exit the neighborhood, yellow probably will turn right, it will exit as well, and green is approaching faster, so it will enter. So you have an idea of the highly dynamicity of this environment. So you have challenges that are related to this, and so you need to see and decide what data sharing schemes you can support with this highly dynamic environment. And then when you build applications, well, you will have data loss. So what application can you build that are tolerant to this data loss? So this is mainly what is interesting in the theory of these networks.
One question: the neighborhood is with respect to, there is an outside unit or something like that here.
Yeah.
So what this with respect to this?
Yeah. Well, you pass, so you will be connected for a while, and then you will lose it.
Okay.
Yeah, it was just to introduce the fact that you have mobile nodes, but also nodes that are geographically static. So it will depend on who is transmitting and receiving. But then in practice, all this theory is used to build what is called not a vehicular network, but an intelligent transportation system. So intelligent transport systems are systems that need to support a set of applications, which can be divided in two broad classes. One is safety, and the other one is the information system. So in the safety class, you can share information about awareness of who is on the road, and this can help you having warnings for your driving function. And also moving towards more interesting application, you could use this connectivity to enable cooperative driving functions. And on the other hand, you have a set of applications where you are interested in receiving data about where you are, the traffic information, a map, or I don't know, infotainment. So these two applications, of course, deal with different kinds of data, which are generated in different places, and they do not have the same quality of service requirements, of course. And so to deliver this set of applications, you are not going to use the same method. So you are going to use infrastructure based on one side for the green part, and non-infrastructure based for the safety information, which needs to be there with a very small latency. And so you have the classical architecture of an ETS system that is as in the picture. So you have a vehicular layer where you have your mobile nodes, you have your infrastructure nodes. They can communicate with each other in an ad hoc way, so without the infrastructure. But then the infrastructure nodes can act as a gateway. So you give access to the backend layer, so you can receive services from a server. So a part of this infrastructure is closer to a mobile network than a VANET, in the sense that we said before. And so we speak about long-range connectivity. So it's the connectivity from the vehicular layer towards the backend, and short-range or direct connectivity, which is the one that enables you to talk with your neighbors with the other vehicles, with the other cars, and with the RSU.
Could I ask
Yes.
a question? So, I mean, it would be a VANET if you would have cars relaying information to the RSU. Otherwise, it's just it's still a cellular network with highly mobile nodes. But I mean, what's the rationale for calling that a VANET?
In fact,
VANET, sorry.
Yeah, in fact, I think the VANET is in the vehicular layer. When you have direct communications, you can call it a VANET. The part that goes towards the backend is a mobile network.
Okay.
You have the RSU that serves as a gateway, so it's right. Closer to a mobile network.
Station, right?
Yeah.
To complete what you said, can the vehicle communicate directly?
Yes.
This is why it's the VANET.
Yeah.
No, they relay information, but so you could have like I mean the safety messages between two vehicles, but still no relaying of this information from vehicle to another one. And I think that's where it starts being a VANET. It's when you do this.
Yeah, you have both, in fact. You can have relaying from one vehicle to another through a third one, like from the blue to the yellow through the red one. And you can have direct communications. So I get to there. I get there in, I think, 2 slides. So this infrastructure here, this architecture is quite old. This is the infrastructure that was tested in a European project that was called SCOOP in its first iteration. So it's really what it looked like, I think, 10 years ago in papers as an architecture. but I take it from here. So this is the first architecture that led to standardization. Of course, you need to standardize how this works, otherwise you won't have a network where every vehicle can participate. And so you have a lot of activity in this sense. And so you have somebody who is doing this in Europe, and it's the ETSI who is doing the standardization of the ETS in Europe. In the USA, you have IEEE that is doing the lower layers of the stack, and the SEA, which is doing the applications. Then you have standardization ongoing in Japan and in China. And the problem is that these standardizations are not always compatible with each other. So you have basically the same system, but you have differences in the syntax of the messages that you are going to exchange, differences in the communication stack, differences in the radio access technology. We will speak about this more in the following, and also differences in the spectrum which is allocated for these services. So one of the questions that I have is, what happens if you want to produce in the USA and sell in Europe, for example, or in any other place? So the first thing that one needs to standardize are the messages that we are allowed to exchange. And so here I'm speaking about the messages that are exchanged on the vehicular layer. And these are the messages that are standardized in Europe. So for the time being, you have two messages. One is called the Cooperative Awareness Message. This is a beaconing message. Everybody on the road in a periodic way is saying, here I am, this is my size, this is my position, my speed, the heading, acceleration. So that, well, you can know who is on the road. And this is used for safety applications, and you can use these messages to trigger warnings when you have an imminent collision with somebody else. All of this supposes that there is a human driver in the car. The second kind of messages are the DNMs, the centralized event notification messages. They are not periodic, they are event-driven. So if you are driving and there is a car stopped in the road, or an accident, or some kind of element that might be useful for the others, you can produce a message. You can send a message to your neighborhood and diffuse this message. This message can travel in multi-hop. The CAM message usually is sent to your neighborhood. The DNM can travel in multi-hop. And of course, it has a relevance which is geographical. I don't care about what happens too far away from here. I care what will happen like 500 meters from where I stand in my driving direction. There is a third kind of message which is almost standardized. I would say the draft is there, but it's not approved yet, so it's not standardized yet, but it will come soon. And this is called the collective perception message, and this is quite interesting. So you have in the pink box a very simplified structure of the message. So it contains all the data concerning the emitter station. So the red car is saying, I'm here, this is my position, speed, and everything. Then it contains information about what sensors are on board of this red car. And then it contains the list of objects that the red car can perceive thanks to their sensors. So here I colored the range where the sensors of the red car can see. So the red car can see the blue, I can see the yellow. So it will put this information in the message. And so green, who is coming and has a building that is blocking the vision of yellow, could be informed about the presence of yellow on the road. okay, this is not a good way to design a merge in a highway, but yeah, this is an example.
So this is very close to CV2X of Qualcomm, right? So this is the 3GPP vision of what it seems. Is the right way to think about it, or?
Okay, I'm not in the vision that Qualcomm has is they use CV2X to power this, and
right.
they probably have some arguments in saying that it will work better in CV2X, and we will talk about them later.
Okay.
But this is an application that is seen as necessary by people that prefer ETS G5 as well. So and by the way, this kind of capability will be necessary to do cooperative driving, because these two guys need to decide together where to go. So yeah, I think everybody agrees that this application is necessary.
Okay, but if I get it correctly, SC has a view of, say, the mandate or whatever vision, whereas the 3GPP would have the vision of the embodiment of that to 5G or 6G.
Yeah.
And but this is the same functionality, but seen through angles which are industrially.
Yeah, I think the functionality is the same, and then there is pushing like on the market for the adoption of one technique over the other. But I think they all agree on what should be the application, and they differ on the way we are going to provide the infrastructure to deliver this application. And ETSI is concerned just with standardization. So all the activity that ETSI does is application like radio access agnostic. So it is supposed to work no matter what is your radio access technology.
Okay, okay. So, but the principle is that you can do that in a purely distributed way, which is probably what certain IC would push for. And
yes.
Whereas the 3GPP
yes.
would have the idea that, I mean, you
yeah.
need 5G to embody that, right?
We get there at the end. Yeah.
Okay. Can I ask a question just to see if I get it right? The left box, it's exactly as CAM?
Yeah.
Okay. So we're talking about a lot of data here.
Yes.
Yeah. Is it a problem?
Yes.
Yeah.
Because I get ahead, but in fact, these messages, you are supposed to share them in broadcast to your neighborhood, and the size of the frame that you are allowed to transmit on the radio interface is quite small. And these messages can be very long, and so you will need to fragment them, and this will be the first kind of broadcast message that would need to be fragmented. Another way to address this problem is to put rules on what you should input in your perceived object container. Not everything you see, but things you see and you didn't communicate within a given interval in the past. So you can reduce the size of the message. But yes, this is going to be considerably larger than CAM and DEMS. Yeah.
Last question is about security. So imagine that red is evil and size to green. Go ahead, it's all clear.
Thank you for this question. We are working on this. The function that tries to spot the fact that people might send you false information is called misbehavior detection. So I'm not going to speak about this today, but I spoke about that last year. So there is a seminar somewhere on YouTube where you can go, or we can speak later with a coffee. Yeah.
One last question. So
yeah.
Here the notion of environment, because everybody perceive objects with environment is not linked to a RSU. It's linked to a car, right?
Yes, and as standardization goes, what you are supposed to communicate on is not environment, but mobile nodes. Mobile nodes. I do not communicate an obstacle that is there, like a building or something that I could see in a map. I communicate information about mobile nodes, and the RSU can do this and should do this because it is supposed to be better placed to have a view, a consistent view of the system. Okay, so I wanted to say something about the stack, the protocol stack that is standardized by ETSI. This protocol stack, it's called ETS-G5. So you have at the bottom the radio access technologies stack. So it's layer PHY and MAC. All this protocol stack is supposed to be radio access independent, but in fact, this was developed having one specific radio access in mind, which was the one that was used to do vehicular communications for the ETS. Then you have a network and transport. The thing here is that you have a geo-networking protocol that is new because information is generated and needs to be consumed in the geographical neighborhood. So what you want to do is to be able to address nodes depending on their position. So this geo-networking gives you this opportunity, and then on top of that, you can run an IPv6 protocol. You have a layer which is called ETS facilities, which is specific to this application as well, because it is the layer that provides ETS specific services to the applications. And it is also the layer that produces the messages. So it is the layer that sends the CAM and CPMs. But the thing that I find interesting about this protocol stack is that finally, it's not really a stack anymore, because you need to have these two blocks, which are ETS management and ETS security, that are completely cross-layer. ETS management, for example, is responsible of data congestion control. So we will see that you will have the problem that if too many people try to send the messages at the same time, the system crashes. And so you need to mitigate these consequences. And there is no action that you can take at a single layer. You need to coordinate your actions across, you need a cross-layer approach for security as well. And so, yeah, the point I guess I was trying to make is that you need to be cross-layer more than in other applications. Yes.
Yeah, so I mean, it is still, it is carrier sense based, right? Sorry? It is
carrier sense based. ETS 822.11, yes.
Right. And so, in that sense, I mean, there is some sort of congestion control.
Yeah.
There is present, which would not be necessarily present in the 5G version of it. Right?
Yeah, but it's not all. Like when the systems, but I have a slide about that later, so I will get there. When the system starts to be congested, there are things you can do, like reducing the frequency with which you wish to transmit, to just ease the pressure on the system a little bit, so that it collapses.
Okay, I see.
Later. And this is a choice that you take at the application layer, for example.
I see. Right.
Then, let's talk about this first radio access technology, which I will call ETS-G5, because IEEE 802.11p is too long for me, but I will be talking about this technology. It has been taught taking the standard for Wi-Fi, that was the 802.11a standard, and starting from this standard, it has been adapted to the requirements that you have in vehicular networks. So you have longer ranges of operation with respect to normal, regular Wi-Fi. You have extreme multipath environments because of the environment where you are going to operate. You have the nodes that can move quite fast. And you have requirements, especially in latency, that comes from your applications. And you need to carry a special type of frame that is a short frame. At the beginning, it was only comms. It was very short messages. So the lower layers, so those that gives you the radio access technology are a modification of this standard for the Wi-Fi. And the most important modification that you have is that you reduce your bandwidth, you cut your bandwidth in half. So you have channels of which are 10 megahertz wide. And you do this because your channel becomes very selective in frequency. And so you need to have a narrowband channel to contrast this problem of selectivity. The other thing that, and of course, this has a direct impact on the data rate that you can send over this channel. And another thing that is that there is not in this standard, but there was in the Wi-Fi, is this mechanism of request to send and clear to send, which is the mechanism that you use when you have like 3 nodes and the 2 nodes at the periphery think that the channel is free, so they transmit. But by the time the signal hits the central node, well, you have a collision, and none of the 2 guys at the periphery could well, they do not know that the other exists, so they couldn't sense the channel as occupied. And so usually you have this mechanism where you, before make a request to send and you receive, well, an acknowledgement that tells you you can send, and you don't have this mechanism in these networks, so you will have a lot of collisions that will be caused by this problem. Yes.
So strict US requirements. So what are these requirements? Because I mean, if you have this extreme multipass environment, this high density, how can you enforce everything strictly compared to what people do in critical systems, right? So
you are right. You are not going to. Yeah, you are not going to pass through. You are not going to route your information. In fact, the way you address this problem is that you send in broadcast, and whomever is close enough receives your comm, and you are not going to route this thing in a network. Yeah, probably that was not the good place where to put this line.
yeah, so I mean, what people would call strict US requirements in mission critical systems in real time, I don't know, type of things that people have done, like this deterministic Ethernet and things like that. That's on a plane. That's what you would have, right? Yeah. So this is just a joke compared to what people have in mission critical systems.
I agree with you.
Like Molos, for instance.
It's
no, even I mean, if you have extreme multipass environment, I mean, its fading is arbitrary. So what can you guarantee?
And you have collisions everywhere.
Yeah. So I mean, that's.
Okay. So the probably what I had in mind was the fact that you do not have HIRQ in these networks. HIRQ is this mechanism that allows you to detect if you didn't receive a message correctly and ask for retransmissions. Of course, it takes time. And so what they did, they cut it out, and that's it. So either you receive the message at the first time it is sent, either you have an extreme multipath environment and you do not, but at the time where this thing was set, the application was, I am driving and my car is receiving beaconing from the other cars, and maybe I get an alert, but I am like driving. So it's not at all the requirements that you have in critical systems, as you were saying before. It's okay. It's relatively strict QFS requirements, but I think with low latency, I was thinking about the fact that took off hierarchy. Anyway, so we started that you work in channels that are 10 megahertz wide. So standardization, you have a band around 5.9 gigahertz for this kind of communications. You have 7 channels. One is called the control channel, and the control channel is, well, the channel where you let circulate messages that give you the right to transmit on service channels. And it also is the channel where you send all these broadcast safety messages, like the CAM, the CPM, the DNMs, all are sent in the same control channel. 10 megahertz is not a lot as bandwidth, so this channel is quite narrow. And yes, the problem that we were speaking about before, the volume of data that should circulate on this channel is a real problem.
So it's actually a mix of a control plane and the data plane?
Yes,
okay.
It is. And everybody needs to listen to this channel, of course. And this is it. Channel contention scheme. The problem is that everybody will want to transmit, and you need to have a way to give turns to people to talk, because if two stations transmit at the same time, the receiving station cannot understand anything of the signal that has been sent. So the classical scheme that is used is a channel contention scheme, which is called carrier sense multiple access congestion avoidance. So the idea is that each station can listen to the channel during a probe period and can sense if on the channel somebody is transmitting on this specific radio access. So they sense the power that is on the channel, and if the channel is empty, they attempt a transmission because they say nobody is speaking, so it's my turn. I can take the channel, I can occupy the channel. If the channel is occupied, they wait a back-off time and then they try again. So, of course, in this setting, you will have times where two stations think the channel is free and so start to talk at the same time and they do collide. Plus, you have another kind of collisions, which comes from the fact that in each station you have 4 different queues, because you have 4 different classes of traffic, and 2 queues might want to start talking at the same time. So you have what is called a virtual collision. But as far as this goes, this is the standard mechanism that is used in Wi-Fi. The point that I want to make is that this system is distributed and asynchronous. So you listen to the channel, you start talking, everybody knows what is the maximum duration of a frame, but there is no set time for start talking. There is no time slot. Then you have this distributed congestion control that we were talking before. So when you start having too many people trying to access the channel, you start having collisions, and every time there is a collision, people will try again to transmit on the channel, and this thing snowballs rather quickly. So what you do, you can operate in different states. This distributed congestion control has 3 states, and depending on how the fraction of the time you hear the channel occupied, you can change your state. And what are your actionable items? You can reduce your transmission power when you sense that the channel is becoming congested, or you can space out the frequency with which you want to transmit messages. So this is the application layer that needs to start generating less frequent messages. Or you can play with the data rate, which is...
What is the difference between the two last? Because,
the data rate is...
I understand what it is, but for me,
yeah,
if the packets are more or less the same size, then they are equivalent.
What I meant is that if you change your modulation and coding scheme, you can transmit faster. So you can occupy the channel for a smaller amount of time. because it was cut in my head. It's, yeah.
Isn't there also a self-regulation? I mean, when the traffic is very high, cars are packed and they don't move, and exchanging messages is useless, right? Or less important. And it's for high velocity and small, and therefore less service density.
Yeah.
That things are important.
I don't know. I'm not very acquainted with the details of this mechanism. So it's possible that depending on the speed you are going to, you can modify your transmitting pattern. But I don't know. I will need to study this standard. This thing is standardized. This is standardized by ETSI. This scheme here, these 3 states are the states that are in the standard, in the ETSI standard for congestion control. The wave version, the ETS system used in the US does not have this same congestion control system. They have another system, but I'm not acquainted.
But is there something? Assume you are completely stuck on the highway with everybody packed. I mean, you have lots of people around, and you see lots of people, especially. And so, why should you exchange information there? Right?
There are okay. 2 things. One, there is some rule on the frequency of the exchange of information that is in the standard, in the protocols, that depends on your speed. And you have a minimum and a maximum interval between consecutive messages, and this is set depending the DCC and also the situation that you experience around you. And the second thing is, I would think that in such a situation, the smartest thing that you can do is to reduce a lot your transmit power so that you exchange only with the very close neighborhood, and you allow for reuse of the channel, well, more reuse of the channel, because but I have no idea if this is what it is done. So
but if I can, so I'm not from the field, but yes, I'm kind of critic with these 2 thresholds. Because first 50% and 40% is like a one finger decision.
it is.
And I would expect that for that type of thing, a kind of continuous behavior would be much more efficient. Like, depending on the exact value, you have a continuous formula that defines how you behave. I don't know, but for thinking of red or like that. So I think just 2 arbitrary thresholds instead of something that slowly.
I agree with you. And the problem with standards is that probably it's not so easy to mandate continuous behavior. So this is what it is in the standard. I'm not sure that, well, probably you can do something which is standard compliant, but is more subtle in the sense that you indicate. The thing that shocks me here is that you go in the restricted state when your channel load is 40%. 40% is not even half of the time the channel is occupied, and you are glaring red like danger, the channel will collapse soon. And this is
That's funny because it does not disturb me actually, because the rate of collisions can go high. Actually. So
this is due to the system that you use to share the channel. But 40% is but we will get there.
Even in a wired network, usually you avoid to go above 50% because you start to run.
Yeah.
And also you have the same thresholds, greater than and lower than for the transition.
Yeah.
It may be some stability.
Yes, we want to avoid hysteresis.
It could be, I don't know, I'm not familiar with the work that
41, 39.
brought to this standard, but you're making very fair points. So now we started talking about what is cellular V2X, which is more of a latecomer as a radio access technology for vehicular networks, because it got standardized in release 14, which is a release by 3GPP, and think about 4G generation of cellular networks. So what you have now is that you have a new radio interface, and actually you do not have one, you get two. So you have a radio interface that is called the side link, and then you can think about the radio interface that does the same thing as Wi-Fi before, that is ad hoc networking between nodes in the vehicular layer. And you have UU interface. It's called UU because the radio technology, the radio access technology, is the same that is used in the uplink of LTE, that connects you to the closest base station. So with the UU interface, well, you can get long-range communications, and you take advantage of the network infrastructure that is there. And on this interface, you're supposed to use licensed spectrum. So it's your operator, it's the spectrum of the operator that is providing the service. So it's the spectrum of the operator that operates the base station. And then on the side link, which is called side link because usually you have the uplink and the downlink, but here you are transmitting towards your peers in the vehicular layer, you use the 5.9 gigahertz band that you use for ETS G5. So it's unlicensed spectrum in the same band that the previous radio access technology. And so what happens here is that I'm going to talk about the side link. So the side link has been developed extending the device-to-device capabilities of 4G or LTE devices. And as in device-to-device, you have two modes of functioning. The first one is assisted by the infrastructure. So imagine the two cars want to communicate over the side link, but they are both in the coverage area of the base station. So the base station can help them because it can schedule. Yes, I didn't say one very important thing. In this radio access technology, you are synchronous. So you have time slots. So you are supposed to start transmission at the beginning of a time slot, and this implies that you are not doing contention over the channel, but you are doing scheduling. You need some kind of algorithm that tells in this time slot, this is going to talk, in the following one, this other node is going to talk. So the scheduling algorithm, if you are in a coverage area, is done by the base station, then sees everything, so it's able to give turns. And so the vehicles will exchange the data on the side link using the turns that have been established by the infrastructure, by the base station. This is very convenient because you don't get collisions and you exploit fully the bandwidth that you have to send traffic.
It is what you meant in the earlier slide when you say that these side links operate with an analog of 802.11. Right? So you then try to avoid collision, but by scheduling.
Exactly.
There is a mode.
Yeah.
Then 802.11.
Then there is a mode where you do not schedule thanks to the infrastructure. You schedule with a distributed algorithm, which is called SPS. And so the idea is that when they exchange data, the vehicles, they exchange like the data plane, but also there is this side control information or side link control information, which is sent with every packet. And this side link control information is what allows to a given vehicle to alert the neighbors of when it intends to perform the next transmissions. Okay, so you reserve the time slots in a periodical way. And so you say for the next 10 time slots with a periodicity of that microsecond from now, I will be transmitting. The other knows that, the others know that, and so they will let you transmit. And so there is this algorithm is complicated. There is also a probe, a sensing period where where you make sure that the resources that you want to reserve are not already reserved by somebody else. There are a ton of parameters that can be optimized in this algorithm, but what matters is that it is distributed and you do scheduling with this time slotting. So of course, when you do scheduling with this time slotting, you don't have the same pattern of collisions that you have with channel contentions. And this gives you an advantage because you reach saturation of the channel later. The problem is that if the system is synchronous, this mode 4 works without the infrastructure, but at some point somebody will need to synchronize you. So the infrastructure is not in the picture here, but needs to be there somehow. Okay, so what are the improvements of CV2X yes, the radio interface. Now you have sub-channels, so it's possible for you to, in ETS-G5, when you transmit a message, the message spans the entire channel, so 10 megahertz for one message. Here you have sub-channels, so maybe you can have 2 or 3 or 4 messages in parallel that go on the channel. You can support several data rates on the side link, the part that is broadcast, because in the side link channel information, you are declaring what modulation quality scheme you are going to use. So this helps you, gives you a parameter more to optimize for avoiding, for example, channel congestion. You get HARQ retransmissions. This is blind HARQ. You are broadcasting, so nobody is going to tell you, I receive it, I didn't receive it. So what you do, you schedule a first transmission and a retransmission few time slots after, and the receiver decides if he needs to decode also the retransmission because it didn't get the first time. And overall, you get a better performance of the radio access technology. So you improve with respect to 802.11p. And the good point is that your spectral efficiency improves. So you use better the spectrum because you don't have this problem with collisions that, in case of congestion, kill you. So the question everybody asks, there is some kind of, as François was saying, there are some actors on the market that are pushing a technology over the other. There are some other stakeholders, which may be constructors or integrators that maybe have experience in Wi-Fi and resist CV2X. And so there is this big dispute on whether actually one is better of the other. So you need to compare the performances. So this is hard, very hard. The first reason is that field tests, you have them, but you have them for one technology or the other. They're usually small, and so you get results that cannot be put side to side to decide which one wins. And so performance comparison usually is done in simulations, and you need to have simulations to have enough nodes to test congestion. And so this has one problem of testing things in simulations is that the parameters that you can tune, especially in CV2X, are many. And so sometimes you compare things, but the parameters are not well tuned, so the results that you get are not really relevant. And so take these comparisons that you might find in the literature with a grain of salt, in the sense that they might not yield the entire truth.
It's really easy to show what you want to show.
It can be. I don't know. I picked one.
So
Yeah.
what is the difference?
Yeah.
Maybe we'll go later on.
My opinion is that you cannot really know, but in the things that I saw, I picked one study that is one that I think is done with some, well, at least, I mean, my opinion is well done and it's really thorough. The references at the end. So they compared the two technologies, CV2X in mode 4. So you do not get to have your base station doing the scheduling, you do it yourself. They compared it using transmission of messages, and they used two transmission patterns. The first one, messages are constant in size and they are truly periodic. And in the second setting, you have messages which are variable in size and are aperiodic. And if you go and track the behavior, the transmission behavior of CAMs in real life, you will see that these CAMs are not periodic. They are aperiodic for the set of rules that we were speaking about earlier. So testing with aperiodic messages and variable size is closer to real life. So here I have the results, and I will try to explain the figures. So you are tracking the packet delivery rate. So here we are transmitting and we are saying which fraction of my messages are received as a function of the distance of the receiving node. And so the violet curve here is ETSG5, and the blue one is CV2X, and you see the CV2X is much, much better. This is tested in a scenario with small, medium density of vehicles and with periodic messages of the same size. So the scheduling system with periodic messages, all of the same size, of course, it does better. Okay, so it's the fact that this system is synchronous puts it in the good place to perform better than ETSG5. And the same thing is true when you go higher in the density of the vehicles. This is the figure at the bottom. So when you are very close, maybe ETSG5 does better, but CV2X is much more effective when you increase the distance of the receiving node.
What does PDR mean?
Yeah.
Packet delivery rate. This is the fraction of packets that are sent and are correctly received as a function of the distance of the receiving.
Yes. And so this is based on information theoretic. So
no,
how do you
this is simulation. This is pure simulation.
Right, but so simulation still, I mean, how do you assess that the packet is well received? And do you do implement? Do you check interference? Do you check?
Yes, you have.
SINR?
You have. I don't remember if this was system level simulation or not. But usually, what you do, you have a simulator that is able to simulate the radio environment. So you have the simulators are quite something, because you need to have a vehicular simulator and a network simulator, and you need to have them play together, and you simulate the effect of the radio channel, and then you know the positions of everybody, the obstacles, and so this is how it is usually done.
But there is also possibly, I mean, I don't, in some cases you may have interference on the short links and the long distance links, right? If they use the same channel, so this is taken into account too?
I don't know. I don't know. And I do not remember what kind of simulator they used in this study. So I can, yeah. scenario was 3 lanes on a highway. So it was a simple scenario, not many obstacles. Yes, 5 minutes. Yeah, I go very fast. So when you have a distribution which is not truly periodic and you have messages that varies in time, you see that CV2X well can be outperformed by ETS-G5. Okay, so when you are close enough, ETS-G5 is probably better. The point that I wanted to make is that it's not at all clear that for the side link, one technology is better than the other. It depends on the study that you look at. This is a very interesting thing that I'm not going to talk about because I don't have the time, but if you want in another occasion, we can speak about it. This is what happens when you try to use the CV2X side link and ETS-G5 on the same channel. And it turns out that ETS-G5 is very badly affected, while CV2X is happy, even if a fraction of the nodes speak ETS-G5. That was quite a surprising result, but this is still the result of the synchronous asynchronous systems. So the synchronous has an advantage. And so you can have mitigation techniques to try to have them in the same channel. I'm not going through them, but they exist. And spoiler, none of them will work unless you change some part of the system. And the thing that I wanted to conclude with is the possibility of having multi-link and multi-radio access technology communications for vehicular networks. Long story short, 5G arrived, so you are trying to standardize vehicular communications based on 5G. You still get 2 interfaces, one that goes to the base station, and one is the side link to communicate with other nodes on the vehicular layer. The side link of the new radio side link, so the 5G side link, will not have the same applications as the 4G side link, so both will stay in the picture for different applications. And what is new is that now you get a connection with your base station that is faster than before, much faster than 4G. And this opens the way to a lot of new possibilities. So the first thing is what happens when you can communicate on 2 different radio access technologies, and you can communicate on these 2 together. So the first thing that you can do, now that your latency communicating from the red to the yellow car passing through the base station is not so high anymore, what you can try to do is to use your multi-link to do things. One is to improve your resilience. So you are going to send your data on the side link, and you can relay your data through relay the same data through the infrastructure. So you improve your robustness. Your data will surely get there. Or then you can use the two interfaces to transmit simultaneously different kind of data, and so you increase your throughput. Or then you can use them to run completely different applications. And the other thing that you can do now that you have a response time from the vehicle to the base station and from the base station back, which is acceptable, you can decide to offload all your data to the edge layer. You can put an edge server close to the base station, or well, close, yeah. And you can have this edge layer provide services to you that can be delivered in near real time, because you have 5G that allows you to do so. And this is, I think, the vision that Qualcomm has. And this is very funny to me because this is not a vehicular network anymore. This is like a mobile network, like a standard mobile network. And the last point I wanted to make, I don't think that in Europe we are at all keen on this kind of architecture yet. So I think the market will decide eventually. But the problem that that all this architecture has is that usually you communicate with your telco operator, which might not be the same of your neighbor. But these services need to be, well, they are geographically dependent, so you need to cooperate with your neighbors. So who is going to provide you the service? Your telco operator, another one? Can the two telco operators talk to each other? Who is going to have the edge? And do you have enough edges deployed to provide for the service in a capillary way? All of these are open questions. This is not deployed yet, so it's very, very early stages. But I think that I will close on this remark that it seems to me that we are moving the vehicular back to the mobile network again. And that's it. Thank you.
Any questions? No.
Yeah, so what is the attitude of the car industry on this question?
I cannot speak for
Europe, for instance.
I cannot speak for the car industry globally. I can speak for a few selected examples that I have close by. And so sometimes there is the fact that there has been an effort in past years to integrate components, ETS, G5 that needs to be tested. All of this is very, very, very sensitive from the security and cybersecurity point of view and from the privacy point of view. So, of course, people do not want to adopt new technologies before having tested them, being sure that they don't pose problems. So you have sometimes this effect here, and then when you build a car, you sell the car, it lasts very long. So changing the technology that you thought you were going to be using for the next 10 years is not so easy. Then there are other actors that are more curious about this. But yeah, I have the feeling that there is a bigger pressure from Qualcomm, which is, to my knowledge, the only actor who produces chipsets and who uses the chipset is still waiting for answers. But I think they need to solve this problem with the operators as well, because even if you use mode 4, like you don't use the infrastructure will need to be there to give you synchronizations and to assist you. So if the telcos don't find a business model, they won't find a solution for this problem of sharing, and the business model of the telcos, I think, is not there yet.
Question from people connected? Other question here in the room? So
thank you, and bon appetit.
Thanks.
Thank you.